Start reading a caption of the picture.
Okay, starting chapter 7 today.
Start reading a caption of the picture. It was too small.
And for some reason it says justify text on the screen. That'll be cool.
Applications.
You have to justify why.
I have to justify why it says application of integration. This chapter is a pretty serious building process. And so to give you a brief synopsis before we get started on what we're going to do, we're eventually going to be answering a simple question. And that is, suppose I take a coordinate plane and I put a rectangle on it like that. Right? Then I take that rectangle and I spin it around the x-axis. What three-dimensional shape would I get?
Around the x-axis?
Around the x-axis, yes.
Cylinder.
Cylinder. Everybody see that?
No.
Okay. Well, if you don't see that, you're going to struggle a little bit.
Yeah, you said that.
But you'll get better.
Oh, okay.
Okay, got it? What if we do the same idea, but I take this little 45, 45, 90 triangle, and I rotate it around the y-axis? Nope. It'll be a cone.
Why do they wait?
Oh, it's like if you this sucks.
Not so bad, right?
No, this is horrible.
Okay, hold on. I'll show you horrible.
Oh yeah.
Now, suppose we take this function
Yeah.
and we rotate that around the x-axis.
It looked like a vase or something.
Kind of, yeah.
Circle.
On top of that, not only will we be figuring out what those three-dimensional objects look like, we'll also be calculating the volume.
Nice.
Yes.
Why wouldn't we?
So this is going to be fun. But that's a couple days away. Today we're going to start with something quite a bit simpler.
Isn't that too easy though?
Just drawing the picture.
Is it easy? It is easy,
Why don't
yes.
you just take the...
It's not a matter of just. It's a little complicated. But by the time we get to it, you'll be okay.
Okay.
We're going to start by justifying text again. I don't know why that's there. We're going to calculate the area. So we start with area first. And once you understand the area and you understand the process, the volume's not so bad. Okay, so you should be able to find the area of the region between two curves using integration. You should be able to find the area, and this doesn't make much sense to you now, but it will as we work our way through the slideshow. And then we're going to go back to that idea of the integrator being the process of accumulating stuff. So today we're going to accumulate area. In a couple days we'll be accumulating volume. So that integral is going to add little things up. And then you should be able to make good scrambled eggs.
Oh, mine.
Oh yes.
Everybody says theirs is the best, but
But mine was the best.
milk or water?
Sour
But not
cream.
a lot of milk.
No, sour cream.
Water. Water makes them fluffier.
Sour cream.
It makes them fluffy.
Sour
Milk
cream?
is
Yep.
gross.
Makes them
2%.
fluffy.
That's like a heart attack waiting to happen.
2% milk in any
Telling
situation.
you.
Wow.
It works.
Right, just
Really?
a little scoop. Okay, I'll meet you in the middle one.
I'll try. I'm hesitant, but I'll try. Okay, so blah 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 blah. All right, we have two functions, f and g, and they intersect.
Now I want breakfast.
And by intersecting, they establish a region. So some of the terminology that you'll hear will be things like an area bounded by. If we were talking about an area bounded by, it would be this whole enclosed area, but we're only going to look at an area from A to B. And it establishes that little pink area, which doesn't really have a name for that shape. How could I find the area of that thingamajabber? Ian?
Be the integral of f from a to b, subtract the integral of g from a to b.
Explain why you're doing that.
Because integrals provide the area underneath the curve.
Okay, and so the integral from A to B of f would give me what?
The all of it, and then subtracting.
By all of it, I'm assuming you
all of
mean
the from A to B.
all of this.
Yes. And subtracting g would give you the region in between the two curves.
So then this would be the area from A to B of G, and then subtracting them, what's your left? Okay, so Ian has just explained the whole lesson, and we're done. Good job, Ian. Everything that I have from that point on just reiterates what he said. We start with, okay, well, some terminology we talked about. Bounded by, we'll talk about a top function and a bottom function. That's not that difficult, but you should be able to identify, looking at the picture, which one is above the other one. That's really important. If you don't have a picture, you've got to figure out some way to figure out which one's up on top. Is it F or G or H or Q or whatever function we're talking about? Then we're going to talk about an interval. So we're going from A to B. Sometimes there won't be an interval because it'll automatically determine an area that you're going to look for or a region that you're going to find the area of. Okay. So as he said, all of this stuff that I have explains exactly what he talked about. So the integral from A to B of f of x gives us this entire thing. Because again, remember, integral is the area under the curve. So from the curve down to the x-axis. Then if we find g of x, that's the blue part. And then if you subtract the 2, you take the big area minus that area below, you end up with that final region. The reason it's so important to figure out what function is on top is because we're going to use this idea of top minus bottom. So that's going to be one of those buzz phrases that you just want to burn into your brain. Top minus bottom, top minus bottom, top minus bottom. In the blue rectangle is the fancy calculus speak describing what we're doing, but in essence we're doing top minus bottom. Ian did an excellent job of explaining why it works. Yes, sir.
If it was still below the x-axis, would the answer still be negative or no?
Yes. But still using top minus bottom. It doesn't flip when it goes to the bottom. You just have a negative area.
Oh, yay.
Oh, that was nice.
Well, it's important. Okay. Everybody see that?
No.
I spent a lot of time on this. It took me a good 4 seconds.
I thought this was.
It changes colors. Yeah, it's just, you know,
Yeah.
nothing but the best for you guys.
Thanks.
Uh-huh. Okay, so when the problems get more complicated, we're going to need a process to allow us to do this area thing over and over again. And the process that we use for the area, we're going to then extend into the volume. And to do that, we're going to use something called a representative rectangle. And you're not going to want to do this initially because it seems like a waste of time. But if you can understand this representative rectangle technique, everything else will be pretty straightforward. It becomes very algorithmic. I've used that term before. You know what I mean by that, right?
Mm-hmm.
Set of steps, do this, 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 and you're done. Okay. So here's a problem. I've got f of x. It's in red. I've got g of x. It's in blue. It's not much different than the problem that we just looked at. This is what we call a representative rectangle. So it's a rectangle that's created from the top function down to the bottom function. And notice that the height of that rectangle is f of w minus g of w. Okay, so we picked a random point in the region that we're looking for at w, and the height of that rectangle is the top function minus the bottom function. That's why top minus bottom is so important, because it tells you the height of that rectangle. Okay, you with me?
Mm-hmm.
How wide is that rectangle?
W minus 1.
Nope. Notice nowhere in the problem I stipulate how wide the rectangle is. How wide would you like to make it? Well, we're going from 1, 2, 3 up to, no, that's not 3, those are by halves. So that's 1.5 up to 3.5. How wide do you think you'd like that rectangle to be?
1.
1. Okay, so if we made the rectangle 1 unit wide, we would get something that looks like, whoops, gotta go down further, that. Think that's a pretty good representation?
No.
Might be a little too fat.
Yeah.
Can we make it smaller?
Sure.
How much smaller?
Half.
Half. Okay, so if we do it a half, then we would get something like that. How's that? Better?
Not great.
Not great. You want to go smaller? 0.
Or like as small as possible.
As small as possible. Excellent. So how do we represent it being as small as possible? What do we want the width of that rectangle to go to? And you said
Approaching 0.
Down to 0. So if I shrink the width of the rectangle down to 0, how many rectangles will I have from here to here? Infinite. That will give us an exact area measurement. So a rectangle that's a width of 1, or a rectangle that's a width of a half, or a width of 0.1 is going to be an approximate. This isn't an approximation system. This isn't an exact answer. Okay, so Grant nailed it on the head. We want to shrink that rectangle so that it has a width of 0. Or that there's an infinite number of rectangles because it's the same thing. How do we represent that? We call the width of the rectangle dx. Okay, dx is an infinitely small thickness.
Yeah.
dx, yeah. Which you know is a differential. And so since the integral is an accumulator, if we can come up with one representative rectangle, and it's called a representative rectangle because it represents all the infinite number of rectangles, and they would change. Rectangles over on this side would be taller than rectangles over here, but it would still be f of w minus g of w. If I use the integral, then the integral will automatically take all those infinitely small rectangles and add them up. Okay? So the process here is figure out the area of one rectangle and then add up all the infinite number of rectangles. And when you're done, you'll have the area of the entire region. Make sense? Yeah. Okay, good.
Yeah.
So we'll do the first example here. Let's see, we'll use, I think we'll use black. I already provided you with a picture, but if I didn't, you'd have to figure out which function is on top. How are you going to do that? Well, you could graph it on your calculator. You could look at your neighbor's paper. You could plug and chug some numbers in. Regardless of what you do, we need to figure out which one is on top. And in this case, the square root of x is up on top. All right, find the area of the region bounded by the graphs of blah, blah, blah. So I didn't give you an interval because notice in the picture, it automatically establishes a region that we're going to find the area of. We're looking for the area of this puppy, this little flower-looking thing. I gave it to you, but if I didn't, how would you find that point? How do you find a point of intersection?
Use a calculator.
Set them equal. Or use a calculator. Yes, sir.
If you did it the wrong way, like if you didn't have a picture and you did it the wrong way, wouldn't you get a negative answer?
Correct.
And then
You would have the right, ideally if you did all the math correctly, except that's the only mistake you made, your answer would be the same. You would just have a minus sign instead of the correct positive area. Okay? Is it safe to assume that you could all solve that and find the answer, sir?
Yes.
Is Tyler speaking for everybody?
Yeah.
How would you solve that equation? This equation here, I'm sorry, I don't know if you, this one that we want to solve for that for find x there. Here, this one.
Square both sides.
Square both sides.
Hey-o.
I like that. What's x squared squared?
Actually, the fourth.
X to the fourth
Wow.
equals x squared squared. Sorry, square root of x squared,
Yeah, which is x.
which is x. Good. Now what? This one right here. Okay, shoot.
You're gonna take out an x.
Take out an x.
Plug in.
What does that look like?
0.
Can you be a little more specific on taking out an x?
Factor out an x.
Factor out an x, not
Okay.
yet. We
So
will.
Oh, okay.
So,
Yeah, yeah.
oh, okay, yeah,
Subtract an x and set equal to
I like that. X to the fourth minus x equals 0. We're doing great here, kids.
Now you're gonna factor out x.
Factor out an x. Okay, good. I like that. X times x cubed minus 1 equals 0. Good. So x would equal?
1.
1.
Or 0.
Good. 1 or 0. I'm glad you got the 1 there. And then the other one is here at 0. So that establishes the points of intersection. How do you find the second number? Also known as the y value.
Plug it in.
Plug it in. Where?
Either.
Either, because it's a point of intersection. Okay. So now we've established we're going from what to what? 0 to 1. All right. So we start with a representative rectangle. You can draw your rectangle wherever you want. I'm going to draw my representative rectangle right there for no particular reason. As we talked about, if I want to find the area of this shaded region, I'm going to take the integral as an accumulator. We're going to go from 0 to 1, because that's our interval, and we're going to find the area of that rectangle. So again, the integral will add up all the rectangles. And the area of a rectangle is length times width, or base times height. What's the height of that rectangle?
G of x minus f of x.
Correct. Which would be?
Square root of x minus x squared.
Good. Top minus bottom, square root of x minus x squared. That's the height of the rectangle. How wide is the rectangle? Grant?
0.
And how are we representing 0? Dx. How convenient. We've decided to call the width of the rectangle dx. It's an infinitely small distance of x, which just happens to be the differential that we need to find an integral.
Wow.
It's amazing how this all works. Thank you for the wow.
You're welcome.
I think you planned it.
I didn't. Somebody did.
Who?
Newton,
Oh,
Leibniz.
good for them.
Yeah. Well, they're dead. They don't really care. They've been dead for a while. Okay, do that. Just if you want to practice a little bit, you could fire up your calculators and use the calculator to find the definite integral, have it spit out an answer. Or you can do it by hand. It's up to you. If you remember how to use the FN int on your calculator. You don't want to rely on that too much as a crutch, but since we're doing a lesson here, we got to move along. It might expedite things. Expedite? That's a word, right?
Yeah.
Expedia, expedient.
Expedite? Expedite? Expedite?
Expedite?
Expedite? No, expedite is the speed. I don't know. It might speed things along.
Expedite's a word.
It is a word, but I don't know if it's the proper word. I mean, you can use words in the wrong location. That are still words.
I think expedite is the speed.
I forgot how you do that in
Math? 9. And you'll get a pretty little picture of the integral. Love it, Chuck. Huh? Anybody else? 1/3.
Yeah.
Yeah.
3. And then
Well, 5, 4.
is that the success dance? Or?
You must have the old one. Yes, he has the old one.
You got the old one?
Yeah.
Like look what mine looks
Yeah. Look at her.
Whoa.
Yeah. That's how we roll here. I don't know how
Sorry.
Grassy does
Grassy,
things, but in
yeah.
this class,
like. What?
go big or go home. You know what I'm saying? Any problems? How about doing this thing by hand? X to the 1/2. Bring, do the okay, and then x squared, and you separate. Okay, good. We don't need to review that, do we? Of course, I didn't think we needed to review that either, but we did.
Might as well.
Okay. Get rid of that. Oh, look, I did the solution already. Draw your rectangle. Okay, so sketch a graph. Draw your rectangle. There it is. That one's green. And then find the area of the rectangle. And then plug it into the integral, which is what we already did. I don't necessarily know if you need this step here to find the area of the rectangle off separately. You can work it right into the integral there. More importantly than being able to get 1/3 at this stage, the most important thing is that you understand the process that we're using here. The idea that the integral is the accumulator, and we're accumulating the infinite number of rectangles and adding them up. Because notice the rectangles change as you move left and right. Sometimes they'll be very tiny when you get close to 0, 0 or to 1, 1. Sometimes they're taller. So that's why it's a representative rectangle. That green guy is representing all the other infinite number of rectangles in the picture. All right, any problems before we move on and complicate things a little bit? We're good. Okay. What happens if the top and bop change? Top and bop? Is that a Justin Bieber song?
Yeah,
It should be.
sing it.
Just
No, you're recording.
I think so. Didn't I hit record? You're not allowed to say Justin Bieber on a recording? Does somebody come for me?
You shouldn't
be. They're coming.
Sorry, what?
They're coming for you.
Okay, where are we? I got a picture here somewhere. Okay, let's look at the picture. There we go. All right, so I've got 3 functions there, and everything seems peachy keen until you get to the y-axis, and at the y-axis, the bottom changes. Top and bottom are fine. Sorry, the top is fine throughout the entire region, but at the bottom, it changes. It goes from blue to green. You have to do 2 separate integrals. So you treat R1 as the first region, do that as a completely separate problem to R2. Okay? Let us begin. I probably did the work already, but we'll do it together just for funsies. Okay, let's start by finding that point.
Point. Well,
The intersection between the red function and the blue, well, oh, hold on, let's back up. Which one's the red function?
X plus 6.
Good. Which one's the blue function?
Negative x.
And then by process of elimination, that's the green function. Okay. Now that we've established that, where does the red function and the blue function intersect? By the way, don't trust the picture. You could count. It looks like it's 1, 2, 3, 4, negative 4, 2. Probably is negative 4, 2. But again, I have a nice accurate graph there, but I wouldn't trust that. Set the 2 functions equal, so. Red and green intersect at this point, which appears to be 2, 1, 2, 3, 4, 5, 6, 7, 8, 2, 8. However, you of course would do the math and set the green equal to the red, like Christmas, and solve. That one, not easy to solve because you've got a cubic. You probably have to use your calculator on that one or count off the graph. And then this one is at the origin, so we're good to go there. Okay, here we go. Region 1. I'm going to use that as my rectangle. What is the area of that representative rectangle, Mila? Are you cold?
Yeah.
Okay. Either that or you're making a fashion statement. She's writing in her clothes. I understand. What happens? Sorry, I can't control the temperature in here.
You could.
Well, sure, I could build a fire up in the front of the room. So you are correct.
That's about it.
There is no easy way for me to control. What thermostat? That's not a thermostat. Thermostat's over there. That big metal plate, but I can't.
Don't you put like a cold?
No, that's an electrical outlet. No. Yes, this is the thermostat.
Put a
put like
cold
the
paper
cold-
towel
yeah.
on.
You put a cold
Like
paper
a
towel on.
wet paper towel. That's
Yeah.
what they do in my other class.
Yeah.
So it feels cold.
And no, that's what that's for.
No, it's
No,
not.
you're
That's
wrong.
an electrical outlet.
Every other class has that.
Look, I got this
Here's
guy over
another
here.
There's an electrical outlet.
I got this guy over here and that guy over there. These are electrical outlets. This is the thermostat.
I don't have another class.
What do
with
you
that.
think this is?
I don't know. I don't have another class with that though.
Stylish.
Do you have another classroom that's got balls hanging from the ceiling? Or a Puerto Rican flag on the ceiling?
No.
That didn't sound right.
Still recording it.
I can edit that out. It's okay.
No, don't.
All right, Mila, back to you. What's the area of that rectangle?
Would be x minus 6 minus, plus 1/2 x,
Perfect. How wide is it?
dx.
And we're going from where to where?
-4 to 0.
Awesome. So R1 is going to be found by taking the area of, we'll keep things fancy here. The area of R1 is going to be found from going from -4 to 0 of x plus 6 minus -1/2 x. All of that times dx. It seems nitpicky, but when you're setting these things up, you need all those components. You need to put the two functions in parentheses so that dx affects all of them. Because remember, this is the height, this is the width. And that gives me the area of the representative rectangle, and then the integral acts as an accumulator and adds all that up. We good? Nice job. Casey, you got the second region. What am I going from what to what?
0 to
Perfect. I'm going to draw my representative rectangle over here. What's the area of that rectangle?
x plus 6 minus x cubed. Minus x cubed. No.
Yeah, no, that's perfect. How wide is that rectangle?
dx.
Done. Good. Any issues there? How could we make it more complicated? Well, there's a couple things we could do. We could turn our rectangles
No.
horizontally.
Don't do it.
No.
Don't do that.
Oh yeah.
Come on, man.
Oh yeah. Oh yeah. There is a reason.
What's the reason?
What's the reason?
Well, I'll show you in a second.
Well,
Okay, then don't look. Cover your eyes, Grant. Any problems with this? You'll notice that once you have it set up, these aren't incredibly difficult integrals to solve.
So then you plug them in, and then what do you do since you have 2?
So then your area, the area bounded by, that area total, if we want to get fancies in our pansies,
Yeah.
would be equal to the area of region 1 plus the area
So you add
of region 2. Yeah, add them up.
So it's
Did you get an answer?
12 and 10. Well, 22.
I don't know. Hold on.
Okay, never mind. I just.
No, you might be right. I just don't know if I have it here. We're going to trust you. 22 sounds good.
I got that.
You got it? Kelly got it too.
Me too.
You might want to look away at this point, Grant.
I'll try and last as long as possible.
Good luck. It's like the Ring. Right, you got that reference, right?
I know the
You watch
reference, I've
the
never seen
TV
the
too
movie.
long, you get that scary girl comes out of the TV and kills you.
Yeah, I know.
7 days.
Yeah, this is comparable to that. If Grant looks too long,
Guys.
Newton will actually crawl out of the screen.
He's dead, so he doesn't care.
Long hair hanging down. Well, exactly, he's dead, so. Still recording, aren't we?
Still recording.
Yep. Blah, 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 blah. Okay, so there's our picture. Now, why would I have to use horizontal rectangles in this case? This particular problem is not too bad, because I could solve for y for both of these. I would do y is equal to plus or minus x, and y would be equal to plus or minus the square root of x plus 4 all over 2. The big issue is, however, if I use vertical rectangles like I did in the other one, I have 3 different regions to work with. I got to find the area of this guy going from top to bottom, and notice it's its own top and bottom, which is kind of weird. And, wow. Switch to filter. This one we can do top and bottom, this one bottom and top. It switches, it gets way too complicated. So it seems like, I see you. It seems like horizontal rectangles are going to open up a whole new can of worms. It actually makes a problem like this easier. Question?
Is it because it'd be 0? Because it's like half is positive, half is negative?
No, it would have a positive area.
Oh.
Yeah. The only thing that changes with horizontal rectangles, the only things that change, I should say, is that we're going to work in terms of y. and it's no longer top minus bottom.
It's definitely not.
It sounded like it came from me, that's why I was freaking out. I thought I had my phone on me. Okay, so we get rectangles like that. One rectangle satisfies the entire problem, so we go from having to do 3 complicated integrals to 1 easy integral. And what does that look like? Well, as it says there, top minus bottom doesn't work, so now we have a new phrase, right minus left. Those 2 phrases, top minus bottom and right minus left, you want to put in big letters in your notes. Draw a cloud around them, maybe some stars, arrows pointing at it, highlight it. Dog-ear the page so you can find it. We're going to be saying that so many times it's going to burn into your brain whether you want it there or not. Top minus bottom, right minus left. Okay, so using right minus left, how big, I don't want to use that term, what's the area of that yellow rectangle? Kat, what do you think?
Zero?
Nope. Here.
dy.
That's part of it.
Y squared minus.
We have to do a little bit of work over here first. So 2y squared minus 4 is equal to x. How wide is that rectangle? No, not dy.
dx.
No.
It's a little bit more than 3, whatever the things.
No, we don't want to count either because that's just a representative rectangle. Right minus left. What's the right function? The red one, which is y squared. Minus the left, which is the 2y squared minus 4. Put that in parentheses. That's the width of that rectangle. How tall is the rectangle? dy. Very nice. We want a very short. Now instead of being a very skinny rectangle, we want a very short rectangle. And we would accumulate from where to where? Dane? If you're working with y's, you're accumulating along the y-axis. If you're working with x's, you're accumulating along the x-axis. So these limits of integration will respond to the differential that you have associated with the problem. Okay. And again, not a bad integral to solve, whether you fn int it or do it by hand. I did that, then solved all this. Okay, this is what we already did. And we get that. Which I didn't do the math, I don't think. Now, how do you plug this into fn int? If you were going to fn int it, you don't plug it in as y's. Well, you could, actually, as long as you stick a dy on the end. But it's just as easy to convert x's to y's. You get the same answer. Yes, sir?
I don't think we ever learned how to do that in grade 6 class. I've been in.
If you hit Math 9 on yours, do you have the fancy one or the Bush League one?
You're the Bush League one.
You have Bush League. What do you got? Do you have the squiggle on there?
Oh, Bush League.
Bush League. All right, we can fix that.
Okay.
I think we learn, but really quickly know the numbers.
No one
It's like,
remembers?
Well, all right, well,
You're speaking
the
for everybody.
majority.
You're making a hasty generalization.
Yeah, us.
You two did not. Okay, that's fine. We can.
Some with commas and.
Yeah.
Yeah.
Just because it's math doesn't.
Yes. Commas.
All right, so top minus bottom,
I know.
or right minus left. Got it?
Yep.
All right. And initially, some of the problems you can do either way. It'll just be easier using one of the methods. You'll see some problems where you might have something that says like x is equal to y cubed minus 4. That's not easy to solve for y, so therefore you're forced into using horizontal rectangles. I don't know, just a picture I found of a woman.
Why?
What did you Google search for?
That is not my mom. No, my mom's not that old.
I was gonna ask that, but I would.
Yeah, where'd you find the?
I understand. On the internet,
For you.
What'd you look up?
old women dancing. I don't know.
Don't we all look it up? Of course.
It's not free time. Yeah, yeah.
Quest scores are online. I passed back all the. I think we're all caught up, right? We got nothing.
No, I'm just.
Everything is taken care of, so we're moving on to day 104. Tomorrow, same lesson. I have nothing new to teach you. Tomorrow, we're going to throw a bunch of problems on the board and make sure everybody's understanding the process. But again,
Tomorrow's
remember
Saturday.
the algorithm. I'm sorry, what?
Tomorrow's Saturday.
I think you
In my defense, 3 people said
On
it.
Monday, we will throw a bunch of problems on the board and make sure that everybody understands the process. Rosie, I don't know, can you? Yes.
I think she is.